Greetings. This is a variant of my APS March Meeting 2010 presentation. I should note that this version has been substantially modified as compared with the original APS presentation. But anyway, the talk is entitled Decay of a Metastable Cylinder Phase via Nucleation of the Stable Lamellar Phase in a Diblock Copolymer Melt. This work was conducted with Rob Wickham at the University of Guelph, and relevant links are in the description. Block copolymers are renowned for their tendency to form modulated ordered phases that are not only interesting from a theoretical perspective, but also have practical applications. Here I've shown the cylinder and lamellar phases that I'll be telling you about today. The equilibrium phase behavior is well known, but also important is how to actually obtain these structures, that is, the dynamics of how they form. If a system starts off in the cylinder phase and is quenched far into the region of lamellar stability, that is, if the temperature is decreased a fair bit, then the transition proceeds via spinodal decomposition, whereby the system becomes unstable to lamellar fluctuations and spontaneously erupts in lamellae. If the quench, however, is less drastic, the cylinder phase remains metastable, and the transition proceeds via nucleation, whereby a droplet of the lamellar phase forms and grows to engulf the system. These images show nucleation events seen in experiments. Simulating nucleation in the presence of a microstructure is no easy task, as it requires accurately representing multiple length scales, often for long times. The simulation needs to be large enough to represent the largest droplets surrounded by bulk, but fine-grained enough to represent the microstructure of the mesophases. Adequately representing the microstructure is important as it leads to anisotropic interfacial structure. Just look at the difference in structure at different points on the surface of this droplet. This structure over here looks basically nothing like this structure over here. The difference in interfacial structure may give rise to anisotropic interfacial tensions and thus non-spherical droplets. This work examines the equilibrium properties of droplets, comparing it to analytical theory, as well as the dynamics of droplet evolution. In this work, we represent the polymer melt by a single modulated field phi of r, which gives the difference in A and B monomer concentrations. We employ the Landau-Brazovskii free energy functional, shown here, which has as local minima all observed phases in block copolymer melts. The relevant parameters in the model are tau, which is a temperature-like parameter, high tau for high temperature, low tau for low temperature, and it's related to the Flory-Huggins interaction parameter, and gamma, which is related to the asymmetry of the polymer. In this work, we use gamma equals 0.04, which corresponds to a fractional composition of 0.46. We studied the evolution of the polymer melt using Model B dynamics to relate the time dependence of the composition to functional derivatives of the free energy functional. Here, eta is a noise term. It represents the compositional fluctuations. We ignore these fluctuations, effectively working in the mean field limit. Our general approach in this work is to start with a metastable cylinder phase as an initial condition, and artificially insert a droplet of the lamellar phase, and then see what happens as it evolves in time. Numerically, we represent the composition phi on a cubic lattice with periodic boundary conditions. The dimensions are chosen to minimize the stress on the cylinder phase. The lattice is chosen with a resolution such that there are 8 points between cylinders. We found that this adequately represents the evolution of the system while leaving the simulation computationally tractable in reasonable times using parallel processing with between 16 and 32 processors. Spatial derivatives are calculated using finite difference, and the time steps employ a fourth-order Runge-Kutta method. Simulations are typically run between 10 to the 4 and 10 to the 6 time steps, depending on what we're looking for. Here I've started the system as a cylinder phase with a lamellar droplet inserted. The boundary shown in gray is the numerically located boundary between lamellae and cylinders. The parameters are chosen such that the lamellar phase is stable, but it's only a little bit past the transition. When I start the simulation, the droplet grows, as one might expect since the lamellar phase is stable. It is, however, not guaranteed that the droplet will grow even if the lamellar phase is stable. Classical nucleation theory predicts that if the droplet is small enough, then the surface tension will dominate, causing the droplet to shrink. If I repeat the simulation with a slightly smaller droplet, this is exactly what happens. I can repeat this procedure, looking at droplets of different sizes, in order to bracket the critical size of the droplet. Plotting the critical size versus quench depth, that is, distance from the transition, we see that close to tau LH, critical sizes are huge. This is what we would expect from classical nucleation theory. Droplet growth is driven by the difference in free energy between the two phases, which acts like a pressure and is obviously quite small close to coexistence, vanishing at coexistence. The surface tension, which opposes droplet growth, is not necessarily small close to the transition. The droplet therefore needs to be large in order for the bulk pressure to overcome the surface tension. Further from the transition, where the free energy difference is large, critical droplets can get quite small. We can compare our results with the analytical theory of Wickham, Shi, and Wang, which does quite well close to the transition. Far from the transition, however, it fails. This is expected, since the droplets that they predict are smaller than the microstructure. Even close to tau LH, however, they slightly underestimate the critical size. This may be because their surface tension was calculated at the transition and may underestimate its true value for different values of tau. Using our numerically determined interface, we can plot the aspect ratios of a growing droplet over time. That is, we can look at the ratios of the length of each axis to the length of the major axis. Wickham, Shi, and Wang predict equilibrium droplets that are almost circular in the xy plane and lens-shaped in the xz plane, and that's what we find for our growing droplets. The horizontal lines show aspect ratios for their equilibrium droplet. The z-axis seems to asymptotically approach the expected value, but the x-axis is smaller than expected. This is, however, a growing droplet, so the aspect ratios at long times actually tell us the ratio of growth rates in different directions, not necessarily the ratios of tensions, which is what predicts the shape of the equilibrium droplet. The deviation from the predicted equilibrium value may suggest that kinetics are playing a role in determining the shape. The difference could also be due to the ansatz used by Wickham et al., which may not perfectly estimate the interfacial tension. If we start with a droplet that deviates from the long-time aspect ratio, as in the previous slide, we find that the simulation starts with a period where the shape changes, adopting the equilibrium shape, and the interface equilibrates. This is followed by a period of linear growth, which validates the often used assumption of constant interfacial velocity. If we zoom in on the interface, we see that the droplet grows by simply rearranging the polymers around it to move the interface over. This process is not expected to change over time, meaning that constant growth makes sense. If we repeat this procedure for different quench depths and we plot the resulting growth front velocity versus quench depth, we find a linear relationship. This is consistent with previous predictions by Goveus and Milner. The linearity reflects the fact that the growth is driven by the difference in free energy between the phases, which is linear for shallow quenches. To summarize, we used the Time-Dependent-Landau-Brazovskii Model to simulate nucleation in an AB diblock copolymer melt. We found critical droplets, we found droplets that grow and shrink, and were able to bracket the size of critical droplets. We found critical sizes that were close to, but consistently slightly above predictions by Wickham, Shi, and Wang. We found that growing droplets were lens-shaped, consistent with predictions. Furthermore, the growth front velocity of growing droplets was constant in time, but this velocity varied linearly with quench depth, consistent with previous predictions. I hope you enjoyed this rendition of decay of a metastable cylinder phase via nucleation of a stable lamellar phase in a diblock copolymer melt. If you did, please check out my other videos and check out my papers as well. Thanks for listening.